Here we are. Welcome to Chapter 8. Now that we've looked at some of the makeup of our atmosphere in Chapter 7, we are moving into what is actually causing weather. We talked about a few things in the last chapter, air movements and humidity, as well as energy. And we're going to look at a little bit more specific ways that takes place in Chapter 8. Chapter 8 is titled Weather, Water Vapor, and Air Masses. You can guess the two things that we're probably going to be spending a lot of time talking about throughout this chapter. And the first section here is about understanding weather. And what we have here is a few terms. Weather is the term that simply means the state of the atmosphere at a certain time and place. That is the current weather. Don't confuse it with the word climate, because climate is the year-round weather typical of a certain place. For instance, today here in Oregon, we might say in our part of Oregon, the weather is sunny with no clouds. However, we might say that the climate, the year-round weather typical of a certain place of this part of Oregon, is rainy. Now, you can see how the daily might not go with the typical year-round weather, because the year-round we're kind of talking about averages, what happens the most in that area, whereas the weather is that specific time period. Meteorology is the study of weather and of the atmospheric conditions that produce weather. And we have people on the newsrooms, on the TV and radio that are meteorologists. They try and figure out the weather for that area. And generally speaking, most of the forecasters, we can predict out to 7 days fairly well. Now, there is still some room for error there. We'll talk more about forecasting weather later on in this chapter, I believe. But yeah, we can only do it to a certain extent because there are several factors that do contribute to the weather. And we have three main ones right here, and just these three alone are enough to really mess with the system if any of them are different from one day to the next. So three major factors work together to cause the Earth's variable weather. And those factors are A, heat energy, which we talked about in the last chapter; B, uneven distribution of heat energy, which we talked about that in the last chapter as well; and C, water vapor, which we talked about in the last chapter. Now, this chapter, we're going to see how all three work together to form the weather. 2, atmospheric water vapor is the source of all precipitation. You cannot have precipitation if you do not have water vapor. All precipitation starts with water vapor. Now, they don't all necessarily end there, but they all start with water vapor. Rain starts with water vapor condensing in the air. We'll talk about that later. Hail starts with water vapor freezing in the air. Several layers. Sleet, water vapor that condenses and then freezes on the way down. Snow, water vapor that actually freezes in the air under different conditions than hail. So, and we'll talk about all those specifically as we get later on in the chapter. But yeah, precipitation is the water that falls to Earth, including rain, sleet, hail, and snow. So just that list again there. And atmospheric water vapor can do quite a few things in the air. We've probably seen it on land, in water, in the containers and stuff. But all of those factors that we see happening with water in other places takes place in the air as well, and we can see different things as a result of this. We're familiar with water as a solid, a liquid, and a gas, and the processes that go between those. Melting is the process of going from a solid to a liquid. Freezing, I have a rather technical definition, process in which molecules of a liquid lose enough energy to become locked in fixed positions. Going from liquid to solid is what freezing is. Evaporation, liquid to gas. And then condensation here is water vapor, a gas, becoming a liquid, turning into liquid water. And we have a couple pictures here just showing evaporation and condensation. So all of these things will affect whether or not the water vapor is freezing, whether or not we're going from freezing to melting, whether or not it's evaporating, going from that liquid to the gas. In Oregon, usually when there's rain, it feels better afterwards. A lot of dirt and stuff is washed out of the air with the rain. In Florida, it gets worse because it's so hot there that the water doesn't actually collect as water on the ground for very long. It starts evaporating back into the air and getting muggy again. So, I mean, unless you like muggy air, but Yeah, so depending on what's happening with the water, which process is occurring at that time, will affect the weather in that area. And yes, here. We say that the air is saturated when water in the air is evaporating at the same rate that it is condensing. Basically, we're not seeing a change in how much water is in the air because of heat and other things that can affect it. The water is evaporating at the same rate it's condensing, so there's no net change. Now, the way we normally talk about that, we don't normally say it's saturated. We might not say that in our normal day-to-day conversation, but we might talk about humidity, which is just in general the amount of water in the air, the water vapor in the air. So we might say it's very muggy, usually meaning high humidity, or it's very dry, next to no humidity, or somewhere in between, just a little bit of humidity. Some people notice it with their hair. If you can see me, I have no hair. I can't notice it that way. And then relative humidity here is a comparison of the actual humidity to the humidity of saturated air under the same conditions. So basically, it's a percent of how much humidity or how much water vapor the air can actually hold. So under those temperatures and conditions, how much water vapor could it hold, and then how much water vapor is it actually holding. So it's a comparison there of what's there versus what 100% would be. And that does change based off of temperature and a few other factors, temperature being the main one. When temperature gets colder or warmer, we can see some things happening with the water. One such thing is dew point. When air cools and it's saturated at this temperature, that dew point is when it's cold enough that the air has cooled and now it's saturated. It's got enough water that it is considered saturated. The dew point depends on the actual amount of water in the air. Air containing much water will have a higher dew point because really we're talking about that point where there's so much water in the air that we can't get any more into the air. And when that water comes in contact with cooler things, plant leaves for example, it condenses. It turns into liquid water on them. So the dew point is when the air cools and gets to that, it cools down to that point of saturation. There's no more water being added into the air, but the temperature cools, and that changes how much water it can actually hold. Below the dew point, condensation occurs faster than evaporation. When the air cools below its dew point, water vapor, under ordinary conditions, will not turn into liquid water without a surface to condense upon. That's why you don't just see really puddles of water collecting. You usually see water collecting on something such as a window, a spider web, mirrors outside, car mirrors are what I'm thinking of there. So, then we have dew, water that touches cooler ground and condenses. In the air, it can happen, but it's not just water condensing to form liquid water. They condense around what's called a condensation nuclei. These are particles in the air, usually dust, that serves as a center the water vapor condenses around. When we're at the dew point, when air is at that dew point, any object that is cooler than the air will have water condense on it. And if that dust particle floating in the air is cooler than the air, then the water will collect to it and actually form a water particle, if you will, where that water is collected around that dust. Now, we'll see some other nuclei here as we go through as well. If we get down to the point where it would actually form a solid, when the dew point, the frost point is when the dew point of air is below the freezing point of water. So it's cold, usually, and it's now below the freezing point, 32 degrees Fahrenheit, 0 degrees Celsius. And so instead of forming a liquid, the water will actually form a solid. And we have the term deposition or sublimation, kind of depends on who you talk to, which one. Our book is using them interchangeably. And that's when water vapor changes directly to ice crystals on an object surface. Normally we think of water vapor as going through a liquid phase and then a solid phase. Or the other way around, starts as a solid, goes through liquid, becomes a gas. However, if conditions are right, it can go from from a gas, water vapor, into a solid, frost, the frozen water. I repeated one there. Dew, water that touches cooler ground and condenses. But we're past that because we're looking at the supercooled or when something is super cool here. This is air is at frost point, but there is no surface for water vapor to crystallize onto. So the water ends up being super cool. It's still water vapor, it's a gas, but it is so cold, if it actually touched something, it would freeze pretty much instantly. But there's no surface for it to touch. So it's just super cool water vapor. And if it does touch something, then we get something like what's in the picture here on the right-hand side. I think those are cranberries, and or hollyberries. And it'll form frost, light feathery deposits of ice crystals. I know they're not cranberries because cranberries don't grow that way. But yeah, light feathery deposits of ice crystals, and that's frost. Don't get it confused with snow or freezing rain or anything like that. But they're usually light, feathery. They might even feel a little bit furry if you were to run your fingers on it. And it's because of the way the ice actually forms as it solidifies. Now, occasionally you can get like you might call it floating frost, or frost just in the air. And that's not because the water just freezes in the air and floats around. It's because there are particles in the air, again, like with the dew and condensation. But it's so cold that instead of having liquid around it, it freezes. The water vapor freezes around it. We get ice crystals, and these particles are called freezing nuclei. If the temperature of the air falls below negative 40 degrees Fahrenheit, water vapor can form ice crystals without freezing nuclei. Basically, they'll freeze to each other. But that's at negative 40 degrees Fahrenheit, and I really kind of don't want to be anywhere that's that cold. I like the cold, don't get me wrong, but that's just a tad too cold. So this is the end of section 8.1. Make sure you answer the science video question, and I will see you in class.